So the software library, this was one of the first. I think if you look now at the description of Codo, it looks a little bit different. Normally, if you write your own application, you have a user API. Here's a user API, and you will just say, give me whatever you have. If you become a PhD student at our chair, maybe you would like to look into the network protocols, platform abstractions, what the computer science, the coding algorithms, how finite fields are done, right? The libraries are there. You can work on them, but this is tricky, believe me, right? This is the hard work. So from your side, if you look from here to the user APIs, the world is splendid, right? And Codo started to say, okay, let's support a lot of platforms, right? And come up with a lot of implementation features. Look at here, they're only part of them now. Recoding was one of them, systematic coding on the fly. You will learn about this now. So, and then we looked, who else is in the ballpark? Who also has a coding library? And there was a guy called James Plunk, it's in Texas. He had two libraries, 1.2 and 2.0 of Gerasure. Gerasure is for erasure codes, right? And this was software, this was hardware implementation. And he was really good, but he used Reed-Solomon. And he was scared away from the research because he used, I think it was the XOR that he used. Because he used the XOR, there was one company in the US in 2013 who got a patent for an XOR operation. It's like getting the patent on a plus. Yeah? We were in Europe, we don't care, right? I mean, honestly. If you come to our university, but the American university, they got scared. There's a patent on that or whatever. There was a French solution, OpenFAC, without discussion, right? That was never really good in performance. But then there was Intel. Intel was interesting because they also had Reed-Solomon, only for storage. They had over 100 engineers, and they always told us they will be better than us. And they are using also their own hardware acceleration. It's unfair, right? They have the chip and their own library. They know what they are doing, right? Okay, and then we had us, and then we said, okay, can we at least be comparable to them? And when we looked it up, what are they doing, right? All of them do Reed-Solomon. Codo can also do Reed-Solomon if you want that. The funny thing is, there's one slide, if I find it, is how we do the encoder. And Morten V. Peterson, who wrote this, did this with mixing layers from Google. So it's like you pipe bits in, and they just go through some boxes. And there are 17 layers. And the difference between Reed-Solomon and network coding was only, I think, was one line. And this is how you create the coding matrix. Fundamental matrix out, random matrix in, that was it. And therefore, you can also have Reed-Solomon there for comparison. It supports a lot of things here, and it goes to hardware acceleration, it goes to ARM, right? Try to ask Intel to go to ARM, right? They don't do this. Multi-core support, etc. pp, simulation support. So there was a lot of things that at the time we built up there. And then 2013, just to compare it, the first one was 2007, right? 5 years later, we got these results, and this was published by a blogger, fantastic news for us. He said, okay, this is the generation size. And here we have Codo, here's Intel, here's Gerasure. I thought you forget about the French solution, right? So they were really good for small generations. Why? Because they're aiming for storage. Has to do something with storage, right? They don't go here. Gerasure was really good here, right? But if you compare it to what Codo did, here or here, you see, oh, Codo is already better. And this was the first time we cracked them with all the improvements. With whatever we could do, there is something sparse and multi-threading. I will tell you a little bit about this later. Now, at the same time, we looked into the coding performance. For example, a Raspberry Pi. Right? We could repeat it. Maybe then the numbers can change depending how Codo changed, but it will be in the same range. And here now you see the throughput over the generation size for 4 different fields. Now, remember, here's not kilobyte anymore. Now we talk megabyte, right? So the other one was down here. So the first thing what you see is, here, if you increase the field size, rapidly you go down. But this, what I said, the optimal prime field, it went up. We found some platforms where the optimal prime field was larger than the binary. That must have to do something with the architecture of the platform you're running it on, right? There's not so much research currently carried out on this, but what you see is the larger the field, it goes down. Now, the other thing is, if you increase your generation by a factor of 2, you halven your speed. Surprising, not surprising? If you remember one of the first lectures where I showed you the coding matrix, what did I say about complexity? It's cubic. Cubic would mean you double the generation size and you only would get 1/4 of the one. It's only 1/2. So of course, if you double the work, you need twice the time. So this impact of cubic is not even there. We did not see it. Later we found out where it is. If you go 1,000 packets together, then the cubic kicks in. But hey, this is beyond what we need at the moment for any of the generations we even know. Okay? So for this, let's say, rather small things below 512 packets that you code together, and you will always go here. Why? If you code too many packets together over a generation, the whole encoding vector will get too big, right? And the encoding vector, you will learn this later, is the generation size multiplied logarithmic 2 of the field size in bits. So if you make the generation too high, that's bad. There's also the problem here. If you take this optimal prime field and you really want to convey the encoding vector, that's not a good idea, right? So okay, now instead of having 40 kilobyte, we have maybe something like 20, near to 30 megabyte per second on the binary with 16 packets, and you see the impact. Now, this is what I told you about the complexity. If you go to, at the time, this was the best phone that we had to test on, right? You can even go to 80. Then a PC at the time, you got 2.5 gigabyte per second. So coding speed suddenly breakthrough. And this came with the software changes we made. There's no hardware acceleration. There's no multi-core. There's no change in the way we code so far. Okay, this is the software side. Now, if you go to Kodo, there's also a getting started example. That's a little bit cryptic because they need a lot of things to write there. But you can ask, hey, Kodo, tell me all your secrets. Which means, what can you do for me? Which kind of encoder do you know by now, right? So, full vector, this is what I showed you before. Full vector, what does it mean, full vector? It's a full matrix where we shoot in the random numbers as an encoding vector. But there's something else, on the fly, perpetual, sliding window, sparse, fulcrum. So a lot of things that you don't know yet, but they will have a huge impact on the performance as well. So on top of what you have seen before, because before, in all of these results, we used the full vector encoding. And what we want to understand now, what are these? This is fulcrum code. This is really an advanced code. We talk about this towards the end. But you see binary to the 8, to the 4, to the 16. We don't have to the 2 in Python. I think it's on the C library you have 2 to the 2, right? Also interesting field. Now, full vector, I told you already. In the full vector, just to tell you what it does, because we were always interested also to understand for ourselves what is going on such a decoder, right? What we did is we said, okay, let me show you, you know her, right? Lena. Everybody who's doing a little bit of computer science or computer networks should know Lena. So we took the picture of Lena and we took a row of the pixels and say, you're a packet, P1. This is P2, P3, and whatever. Then we went to the encoder and gave them all the packets. And then we said to the encoder, give me a packet. And we put it here. And another one, put it here. But while we put it there, what we did, we already started while we had it, because why should we wait? We tried to clean up always our metrics. You remember this? 1, 1, 1, the 0 in the upper triangle and the zeros on that. So we wanted to get the pivot elements at least, as we are getting it. And suddenly, so towards the end, you have to wait, and when you have enough linear equations, boom, there's Lena. Okay, what does here happen? You see this? This is showing you the decoder matrix, right? The matrix for the encoding vector, or for the encoding vector that you are cleaning up on the runtime. You don't see the payload. This is the payload, okay? We always show you the payload, what happens here. And this happens on the encoding vector, where the white spot means a 1, black means 0, and you see the gray points over here, how they change. We try to make it only with colors for you, that you understand what's going on here. Now, later you will see a little bit more. If you go to the code library in C++, you can really ask encoding vector by encoding vector, and ask even the decoder, show me what you have, how did you clean it up? Now, one thing, 2009, right? First time. And we looked into the picture. This one was a little bit disturbing for us. Why? Because we could see Lena. And do you remember what I told you in the beginning of the talk, why we should use linear network coding? Because we say, hey, if we have multiple passes and we have linear equations, as long as you don't have enough equations, you will not be able to solve it. If you now go to the privacy and data security chair of Thorsten Struve and say, is this secret? You'll say no. It's not secret. Okay, you don't have the data, but if there's a picture of me and Lena, you always say, this is Lena, not Frank. This is Lena, not Frank. And if it would be a secret, you would say to 50% you will spot Frank or Lena, because you don't know what it really is. Here you see something. Yeah?
But that's mainly because it did not do any source coding.
Yes and no. Something happened here, and we always came and said, what do we have to do here? Do we need some extra security to protect it? It's a good question. We come back to this. Why on earth does this happen? Okay. So, nevertheless, for the time being, just remember Lena. The real questions we had is, when we looked into this and we compared these full vector encoding, we had binary and we had the others. The question was, why is the binary so much better than the others? What is it really? Is it the number of elements that we have, only 2 elements? One of the reasons, we thought about it, and sometimes you do mistakes, right? And before, what is the next? Yeah. So we thought about this problem. First we had only pictures. Then we said, oh, let's do video. Let's be cool now. Now we do video. And Nokia gave us some Linux phones. They were big like this, and we're the first one with Linux phones. We felt pretty cool at the time. So we said, okay, let's broadcast video here and do exactly the same with video. And suddenly the whole Linux terminal broke down. Why? He had to do MPEG-4 decoding for the video and network coding. Too much for the little bastard. It did not really work. So what could we do? And I said, I have a great idea. Instead of taking the packets and send them in a coded way, let's do something different. We just say, we send out packet by packet, put it in the right spot, and when there are losses, and here you see losses, before then you did not see losses, because when we did not get anything, forget about it. We take the next linear equation and put it here, right? But now we say, okay, once we get it, we just put it in the right spot until we are in the end. And then we are filling in the equations. So when you look at your coding matrix, in the beginning everything was randomly filled up. Now you would see a thin layer of ones going through them. So a lot of zeros, a lot of ones, not only one per row, systematic. And then in the end you get random equations. But the amount of equation was less that you have to solve. So if you see the same, so here you see how you fill in the random ones. Once you have filled up the whole rows, you do this. And suddenly we did this with the video and it worked on the machine. I was pretty proud of myself that I came up with the idea. Then we went to Muriel, to MIT, and said, hey, look what we found. And she said, it's called a systematic code known since the 50s. Okay, good. What can you do? We re-engineered it, right? A friend of mine would say, I still consider this to be my idea, but in this case, it was really too late, right? I mean, if it's more than 50 years, people know about this. But what happens here, it's the same thing as before, right? You are sending this is the first phase with systematic, and then you just, I can show it to you again. These are the ones, only zeros here. And then you shoot in random linear codes here, and it's very easy to solve that. So the binary code and the systematic code had one advantage over the other codes. And this is the amount of zeros in the matrix. Who of you is playing Sudoku? Only one guy, me too, so the old guys. If you're apparently above 25, you don't do it anymore. But if you play Sudoku, there is something called kamikaze and something for beginners. The beginners have a lot of numbers, so it's easy to spot what you have to do. The kamikaze is very hard to solve. And the comparison to that is the zeros are the given numbers. The degree of freedom goes down. So you know already what is there. If it's a 0, you don't have to care about it. It's a 0. Applause. We can work with that. We can shift maybe. So putting in zeros was a great idea. So the binary had it by definition. The systematic also had it by definition, so to speak. Now the question is, let's think, we said random, right? What is random? You don't know what random is. So if I take a dice with a lot of more zeros, right? I give you a dice not with 256 elements, I give you a dice with 512, where half of them are zeros, and then you start to dice. Then you have a random matrix, but half of them are zeros. Is it a good idea? Is it a bad idea? I think this is what we talk next time. Now we are going to the magic cube of the encoding matrix, and we say, we know what to do here to make it really interesting, right? We make it low complex, we make it faster decodable. There is the work what I said before. Let's go back to the source code. We've done that. Let's go back to the information theory part, go back to the whiteboard and do that. Our cooperation with MIT is so successful because we talk always on both sides. The one on the theory, the other on the practice side, and you understand, can you do this? No. Can you do this? Yeah, well, let's try that one, okay? And now we are starting to dig into the coding matrix. And this coding matrix has a lot of potential for us. But this we will talk in 2 weeks' time, right? Okay, in 2 weeks' time. Thank you very much.